Good evening. I am Johanna Koljonen and this is Crosstalks. This show is a collaboration between Stockholm University and KTH, the Royal Institute of Technology. And if you have not seen any of the previous episodes, do have a look around the website. We have had shows about robotics, the universe, and how humanity will have to cope with possible global environmental disasters. In other words, these days Crosstalks is just like any night at the movies. If you would like to ask questions of the participating professors tonight, a live chat will open straight after the program is over. You can also discuss tonight's topic on Twitter using the hashtag Crosstalks, as usual. Now we will dive deep into the world of statistics and mathematics. In an era of algorithms insinuating themselves into every aspect of our everyday lives, and more information than ever before existing around us, the need for mathematical and statistical knowledge is becoming ever greater. How can mathematics help us? And what will we learn about human behavior when new and vast amounts of data can be efficiently summarized in elegant statistical conclusions? Here with us to discuss these questions are Mats Boij, Professor of Mathematics, KTH Royal Institute of Technology. Welcome.
Thank you.
Gebrenegus Ghilagaber, Professor of Statistics at Stockholm University. Welcome. And Anders Forsgren, Professor of Optimization and Systems Theory, KTH Royal Institute of Technology. Welcome. Please give our professors a warm round of applause. Anders Forsgren, in your research, you're working with something that greatly affects how we deal with one of our most feared diseases, cancer. How is this related to mathematics?
Well, if you treat cancer by radiation therapy, then you send particles at high speed or high energy to sort of kill the tumor cells. And that's sort of well known. Sort of physics was less well known is behind this application is sort of sophisticated optimization routines to ensure that when you send your particles, you have a gantry, and then you have in the gantry head you have something called collimators. You can form your beam. And then you can sort of, by optimization, mathematical optimization techniques, then you make sure that you get the treatment which sort of is the best possible in that it sort of kills the cancer cells and spares the healthy tissue.
So you form the beam, the shape of the beam,
right.
Essentially, to match the shape of the tumor.
Yes, but it's not that simple. I mean, basically, but if you do it, even experienced user, sort of a clinician, cannot sort of compete with the mathematical routines that you can actually by optimization do it significantly better.
So what comes out, I'm trying to understand,
Okay.
So what comes out is a program, essentially a tool that will help the clinician
Right.
define the goal somehow and then apply mathematics to optimize
Yes.
the beam.
Essentially the clinician says what he or she wants. And that's something that you can normally not achieve, but you try to get as close as possible.
I think this is fascinating, but I have an immediate follow-up, which is how did this come about? As if you're doing research into mathematics, how does your mathematics end up inside the machine, if you pardon the childish question?
How it ends? Oh, well, that's a long story. This is that's research that was done at the Karolinska Institute, and then it was a KTH student. He did his master thesis at Karolinska, and then he also got his PhD at Karolinska, and then he founded a company. And that company, it's called Research Laboratories. They manufacture these sort of optimization systems. So there are other companies, but they are among the world leaders. So inside the treatment system is their mathematical optimization routines.
It's very exciting. Gebre, you're a co-author of a newly released book called Advanced Techniques for Modeling Maternal and Child Health in Africa. What are some of your findings?
It's a joint work actually together with some colleagues, mostly with background in Africa. And what motivated this work is actually surveys called demographic and health surveys. Previously, when one was interested in health indicators in Africa, the methods that were used to estimate these indicators were based on the assumption that there is not enough data, there is defective data. So one has to develop methods called usually indirect methods to address this shortage of information. But since some 3 decades ago, there have been worldwide surveys called fertility surveys, demographic and health surveys. Unfortunately, they have not been utilized. Those data sets require advanced statistical methods in order to exploit maximally. If one is to implement policy interventions, then those data sets need to be analyzed with advanced statistical methods. So this volume is a sort of collection of various advanced methods. Among other things, we address spatial issues. For instance, in modeling child mortality, it's not enough with mother characteristics or child characteristics, but one has to take also neighborhood effects in the sense that geographical areas that share boundaries may share similar environmental parameters.
But you're saying that these surveys have been done for decades, and I think it's shocking that we wouldn't have used the best data available to look at these issues. So that already, of course, perhaps shows how naive I am. But I'm curious about the statistical methods that you have developed. How are they Africa specific? Would it be possible to take the same statistical methods and use them everywhere?
Yes, strictly. I mean, the methods are actually universal. In the sense, why there was this specific Africa term was because the data analyzed in that book comes mostly from African. Actually, entirely, the data refers to demographic and health surveys in African countries. So that's what makes, otherwise the methods are universal.
I think it's a positive development also that this knowledge that has been developed for this specific environment will be used. I'm assuming to get better health information globally.
Of course.
Yes, that's great. Boij, can you describe why you are so fascinated by mathematics?
Well, apart from all these wonderful applications, I think that mathematics has its own inner beauty, and that's what's been fascinating to me. And it's like having a parallel universe around, and you can go there and you can define your own laws of physics, and you can play around and see what the consequences are. You can see what structures build up when you do different things, and also the ideas about abstraction, generalization, specialization. So you study something very concrete and do this for a few examples, and then you see some common patterns. You make an abstraction, generalize, and then you can see something in the above structure here, and then suddenly you can take it to a completely different area, and you can see consequences that you wouldn't have thought of, but they came from the same things that you discovered above. But do you see what I mean?
Yes, but when you're talking about operating with mathematics in this private universe, and then you're saying, and then in this other part, then you're still talking about the abstract, about the mathematical space.
It could be applications still. I mean, it could be applications, or it could be applications within mathematics. But it's all tied together in this mathematical universe. But if you just see each of them in their own context, you might not see the similarity. But when you strip it from all the unnecessary details and stuff like that, and you make the abstraction, then you see other things that you wouldn't see before.
So my academic background is in literature, which of course is quite different, and it has different kinds of goals. I think that in the field of literature, optimally, you are producing understanding, perhaps, but I don't think we make claims to truth. When you resolve something in maths, have you find out something about truth?
Well, that's a philosophical question. I think, of course, it's truth within mathematics, but whether that truth extends outside of mathematics, that's not so clear. I mean, that's the connection between our mathematical universe and the actual physical universe that we experience.
Gebre, I have to ask, another one of your studies has looked at the risk, or perhaps chance, depending on the situation, of couples breaking up. So you're in a relationship and then you stop being in a relationship. And there are statistics around this. Can you elaborate a little bit about this and what you found?
The type of models I usually use in my everyday research are duration models. Duration models in the sense, how long time does it take until a certain event occurs? And this type of models can be applied in lots of areas where duration is of interest. So that in demography, in family demography, how long does a marriage survive? So how long does it take until a marriage breaks up? And what factors affect? How does, different categories of people differ in this? And the issue which I studied was, actually it was a long time ago, the meaning of cohabitation, this informal cohabitation. Which type of couples have higher risk of breakup? Those who marry directly, or those who first live together in a form of informal cohabitation and then marry formally? So sociologists may have their own theory, and ordinary persons may think different things. And the role of statistics is to collect the relevant data and then analyze it appropriately and come to empirical evidence. So what that shows is that the models, which are applied also in the book, were applied to model differentials across what you call different categories of people. So what it shows is that it's not couples who marry directly, as ordinary people might think. Rather, it is the people who first live in formal cohabitation and then marry that have higher risk of divorce.
Higher risk of divorce if you cohabit first.
Yeah,
that is
in this, and this is well documented actually, not only in Sweden but in different countries also. And that takes you to another topic known as what is it then? Once one has found this empirical evidence, then one tries to explain what is this, what makes it, and the answer one gets is that this is selection, we call it. Technically, we call it selection. It means that the type of people who go to direct marriage are not representative of the entire population. They are a selected type of people who are more conservative, possibly, and this very character makes them also to hold difficult situations also.
But then I have to ask, I guess I have to ask all of you, when you are working on something very concrete, like when you're working on solving the problem of optimizing the radiation in the cancer treatment, or when you're presented with a demographic curiosity that you want to nail down the truth on, are you working in the abstract mathematical space? Are you going to work thinking I am now going to work curing cancer? Or is it I'm going to work to deal with these very exciting mathematical problems?
Well, I guess it's both. I don't know much about the cancer. I have to talk to people who know that. So, because I could work on a very exciting problem, and then I'm very happy I go to talk to them, and they say, okay, that may be interesting mathematically, but it's of no use to us. And then I have to go back to my drawing board. But it's also the case that sort of what comes in from the applications makes me think differently on the math. So it sort of goes both ways. But yes, I think I'm in the math world.
What about Gebra?
I agree with Andres. Suppose I think some types of study are theory-driven. You have a theory, and you want to test if this theory is true for a certain given data, or you may have to simulate different types of data to test that theory. Other types may be more of exploratory. You have a certain data set and you explore it. This is what you call data mining, in order to get some what you call patterns and develop a theory from that. So in my case, I am more applied statistician, and I work together with some people in the substantive areas, be it demographers, sociologists, or public health experts. So I help them methodologically, and from the what you call theory that is already established there, that gives me an idea what type of methods are appropriate for this. And from these methods that I give, then one gets what you call new substantive theory or new theory also. So it's both interaction from application and from theory.
Mm. Do you work applied at all?
No, not really. but I'm at the engineering school in Stockholm, so that means that I actually have to think about what the students should use the mathematics I teach for, which that's the area where I think about these questions mostly.
We're going to return, for instance, to data mining, but let's now welcome our guest via Skype. David Spiegelhalter is the Winton Professor for the Public Understanding of Risk at the University of Cambridge. Welcome to Crosstalks.
Hello.
Hello, Professor Spiegelhalter. Last year you published a book called The Norm Chronicles, which seems both hilarious and really terrifying. Could you tell us a little bit about this book?
I should first say that my co-author was a literature graduate. So this was a collaboration between someone who's trained in literature and me. I'm started off in mathematics and now do statistics. And the whole idea was to try to bring together a mathematical statistical approach with an approach based on stories, narratives, and feeling people's. So the idea is to sort of humanize statistics, to look at the boundary between the kind of analysis that you're talking about and ask us as humans how we feel about it.
As humans, how we feel about statistics. So you're talking particularly about chance and risk, and you're claiming that these are not all about numbers, but quite a lot about feelings. Can you elaborate a little bit on that?
Of course. I mean, we're human beings. What we're worried about, what we get anxious about, what we fear is got very little to do with, you might call, the probabilities of things occurring. You know, maybe we get worried about things we shouldn't be worried about, and we don't get worried about things maybe we should. But I don't like to try to tell people what they should be worried about, and we don't do that in the book. We just explore all the different things that we experience in our lives, from birth to transport to radiation, having X-rays, to what we eat, what we drink, drugs, sex, sport, a lot. All of these, can carry bad consequences. And there's we're all uncertain in our lives. And how can we use statistics to maybe give us some idea of what the consequences might be?
So the consequences. So I'm starting to understand now. This means that that understanding that the mathematical, you want to do a thing X, and then that has this statistical probability of some particular consequence. But that information, of course, is not enough at all to make a good decision about what to do, because there might be other consequences, positive consequences, for instance, that you're not taking into account at all. Yet it seems to me, again, as a layman, a little bit unscientific to say that, of course, we have mathematics, but then there are all these feelings. Mats or somebody, would you like to comment on this?
Well, I think maybe this is an instance where people in everyday life can actually make a change in their behavior if they have some knowledge of statistics, some knowledge of how to make mathematical reasoning, how to have a feeling for numbers, not that the numbers are important, but that they get a feeling for whether 100 is much more than 10 or not. I mean,
Anders?
Yeah, well, I don't know. Is math the truth? I don't know. If you give people probabilities, they will not, as you say, I don't think we are that rational. But it certainly helps if you can do sort of some mathematical thinking, and, well, it helps your reasoning to make it more clear.
So, but we're saying, I mean, obviously we can understand systems quite well by looking at statistics, because the average is a sort of a factor here. For instance, we can learn things about public health by looking at statistical information. But is it possible to take this statistical information and do something with that in the life of one individual? Or am I thinking wrong if I'm saying that I would like to do that? Gebre is sighing. That's a sign that it's not possible, or?
No, well, if I am to connect with the earlier statement, I would like to say that statistics deals with trying to quantify uncertainty, to model uncertainty. So one cannot be 100% sure, because usually in statistical studies are based on a sort of a sample and try to generalize over a population. So one cannot be. So what different researchers in statistics do is to try to develop methods that can, what you call, press the information that one have and get the best out of it, to minimize this uncertainty, to minimize the risk of making errors. So one cannot be 100%, and as was said earlier, once you have such information, when new data comes, it's possible to update it and build on previous information.
So, Professor Spiegelhalter, would you say that it's possible to use statistics to live more healthy lives, for instance?
I mean, that's what I'm really interested in, because I advise on the design of information leaflets for patients who are facing difficult decisions, and how to communicate risks about floods and things like that. And you know, as people have been saying, the panel have been saying, your statistical work just talks about populations. They just talk about averages. And so, strictly speaking, we can't say this is your risk to any individual. I mean, I can put my details into a computer program. It will tell me I've got a 12% chance of a heart attack or stroke in the next 10 years, and maybe I should take statins. But actually, you know, who knows what my risk is? You know, I don't know, and nobody knows. But it's probably, if I had to make a bet, it probably would be round about 12%. Now, of course, it doesn't tell me what to do.
Well, that's the thing. That doesn't actually tell one what to do, unless you read the newspapers, in which case it says that you should absolutely not do whatever the thing is. But I mean, like most sciences, I guess statistics would be a sort of mathematical reading of the past. I mean, most sciences deal with the past. But statistics is quite often used to point into the future, to try and predict the future. Do we have any reason to believe that statistics is in fact a method to foresee what will happen in the future?
Well, I think that Nate Silver's recent book, Signal and the Noise, is very good on this, because he uses past data to try to make predictions in sort of well-controlled situations, in sport, in politics, and so on. And he emphasizes that what you should not try to do is make a prediction. What you should be using your data for is to produce good odds, essentially good betting odds. You know, what would you bet on these things happening? Who's going to win the election? And actually, those ideas can carry right over into health and into everything. What would I bet on me living till 80 to 90? Well, I could actually produce some pretty good odds on that. And, you know, that's what you do when you buy life insurance, or have pensions. So the insurance industry is doing this all the time. This kind of thinking to produce good odds.
So better advice rather than prophecy. And the problem is...
Yeah, exactly. But it still doesn't tell you what to do.
No.
You know, you could be reckless and ignore the odds if you won, or you could be really cautious and get very concerned about small probability, small chances. So it doesn't tell you what to do, but it actually, what it should do is enable you really to take responsibility for your actions and not to be reckless.
Thank you. Gebre?
Well, I agree. This is the thing that we need to know. I mean, the empirical evidence that we get are more what you call aggregate. They apply for the entire population or based on a sample. So it doesn't point out at an individual. It may say that 80% of treated patients are cured after a certain period, while only 30% of uncured patients are what's called free from the disease after a period. So this says a general aggregate information that 80% of the cured and 30% of those not cured. So one can draw a conclusion from this that, okay, this treatment might help to what you call elongate life. Okay, but this doesn't say that such an individual will have a longer life and such individual. So it's not an individual base, rather it's an aggregate. So that's where it comes. But when it comes to this prediction, I don't agree with this description of statistics that it is about past history. Well, like statistical office produce some reports based on what has happened last year. It's okay, but statistical methods are devised to what you call model past history in order to be able to predict for the future, especially in time series data.
Yeah, Mats would like to come in.
On this particular...
You looked as though you had something on your mind.
I was just thinking that, I mean, we're talking about this implications and stuff like that. I mean, you see correlation, you see that you do something and something else happens. That's a cause and effect thing, and then you see some correlation in your statistics, and you can think that this is maybe a cause and effect thing, but maybe it's not. I mean, maybe it's just a correlation that same kind of people do this, that do this, and it's not really related in itself.
And there's not a huge understanding of this in the general population, I should add. We're going to talk a little bit more about that in a little while, but we're going to let in a little bit more maths. A remarkable story. 10-year-old Linus Hovmöller helped his father, Professor Sven Hovmöller, 3 years ago with a complex scientific problem by using advanced mathematics. Together, they discovered the atomic structure of a type of crystal called approximants. And here they are with us on Skype. Welcome, Sven and Linus.
Hello. Hello.
Hi. I have to admit immediately that I do not understand the words that I just said. So I don't know what it is that you achieved, but it's a chemistry problem that you solved. Could you tell us a little bit about what you did? Sven, for instance.
Yes, we worked on a crystal structure of a complex metal alloy, so that's a mixture of different metals, and they show tenfold symmetry, which has been proven mathematically that material cannot have tenfold symmetry. But nobody remembered to tell the metals that they couldn't be like that. So turned out they were like that. They was discovered by Schechtman some 25 years ago, and he got the Nobel Prize for this 2 years ago. So it's a big discovery, and it's been very difficult to solve the atomic structure by normal crystallographic techniques.
So how did this? What is it that you did? What did Linus do?
Well, we looked together at electron microscopy images and electron diffraction patterns, and showing this tenfold symmetry. And we also used the computer to do some processing with advanced mathematics like Fourier transforms. And well, we got lots of different patterns, and actually there are a whole series of compounds that are closely related. And I think the main thing what Linus did was that he helped to sort things out, and he's pretty good at seeing, understanding patterns. So I've been working on this problem for about 8 years with the same data, and without result. You know, always feeling I'm almost there, but I couldn't solve it for all those years. And then once I asked Linus and we sat together, working 2 whole days, then we could solve it.
I love that. There are kinds of, so this is a kind of pattern recognition problem in part, and perhaps being 10 years old actually was helpful with that. Linus, you are 13 now, and you have chosen to attend a specialized math class at school. What is it about mathematics that you find fun?
Well, I don't really have anything specific that I like. I just like maths in general and stuff related to math.
Mm. What do you plan to do with mathematics in the future? Are you looking at a career somehow that involves these skills?
Yeah, well, right now I'm not really sure, but I think I might go into some science or like chemistry or physics branch, but I still want to do something with mathematics.
Are there some particular problems that you're curious about solving in the world? Is it going to be more crystals or something else?
Well, I'm not really sure right now. Maybe I'll decide in the future.
We're going to talk a little bit later about, or very soon indeed, about maths educations and the general knowledge levels of the sciences in the population. Sven, do you think that the home environment was particularly supportive of maths in Linus, or could any 10-year-old potentially help with science on this level?
I think many 10-year-old could. Also, but I do think Linus is quite gifted in mathematics and logics and patterns. For example, one thing made me quite amazed was we together with my wife, Linus' mother, we published a book a couple of years ago and he saw a misprint. The editors had done something funny with the electron microscopy image on the front cover. Nobody had seen that before. But Linus just spotted it. So he's pretty good at patterns. But of course, at home we discuss mathematical or logical problems rather, and things like that. I mean, I go through logarithms with my kids when they're 5 years old, and things like that.
Thank you so much for joining us, Sven and Linus Hovmöller, and thank you for your great work. Thanks.
Thank you.
Bye.
Thanks. Bye.
That's pretty fantastic. I have to say, not in my house so much logarithms with the 5-year-olds yet, so that might be something I'm doing wrong. Mats, should governments across the globe be concerned about the knowledge levels in mathematics? I know you feel passionate.
Yeah,
about this.
I think they should be aware of the problem that mathematics is not taught in a way that attracts the interest of young people of today, so that fewer and fewer young people want to study mathematics on a higher level. So that will be a challenge for many countries to keep up with the technological evolution that we have if not enough people can contribute.
It's so curious, because it would seem that these problems, I don't know if we actually know less mathematics than we did before, but certainly relative to the need, we just don't have a sufficient base of people who have these skills coming into universities. For instance, everybody across faculties are complaining that undergraduates just don't have the math skills they need. Gebre, you're nodding as well. Yeah.
Well, it's true.
Yeah.
I mean, I agree.
How should we go about solving this? You have all chosen to work with these fields. What is it that drove you that could be bottled?
Well, it's nice to do optimization, to do things the best possible way. I think that's very appealing. You can show, I mean, okay, it's not truth, but it's true in the mathematical sense. And it's also very nice that you can solve real or work on real problems, and so the numbers, they do mean something. And that may not be important to Mats, but to me it's very important. The numbers, they have a meaning.
Actually, and also the satisfaction that something is just right. I
Yes.
think that is something that should be possible to communicate to young people as well. Even just, I mean, in this case, of course, that was in particular, there's something wrong with this image, or this line would complete this image. Those kinds of visual problems are mathematical problems, and I guess not everyone is aware of that. David, what would you suggest to inspire more people to seek out these fields? Should we?
I don't know. I mean, people are very different. I mean, some people are attracted, and kids in particular, to the beauty of maths, to patterns, to structure, to games, to fun. And there's a lot of maths teaching that does that, which is great, to arouse that enthusiasm for, really quite abstract ideas. I think as people get older, they might get, I would hope they get more interested in the way things work out in the real world, and the way that numbers are used in numbers and concepts of uncertainty and other mathematical concepts are used in real life, in politics and in health and climate and so on. And some people will be much more motivated by those ideas.
We hear now very much in the sort of public discourse about big data, and certainly it's a fact that there is more. The amount of data in the world is growing incredibly fast, and we have better data sets than we did before in a number of fields, and we have new data sets on things that we haven't even intentionally measured. We have just accrued this data because we were trying to do something, use the technology for something else. From your points of view, in your respective fields, what does this make you think? What should we do with this? Are there any worries or directions that we should think about, Mats?
Well, I think that of course we don't know yet what we will be able to do in 10 years or so, and it's so far it's been very easy to, as you say, collect data, store the data, but it's hard to analyze it and make the good use of it. So that's where the mathematical challenges are, to develop methods to see how to dig out the best thing from this data. And of course, that there's this huge ethical issue too, that we collect all this data that might be used in a way which is not good for us. I mean, so that gives us some problems also.
Gebrenegus.
I agree with Matt, Simon. What we need is to canalize so that we get the best out of it. I would like to draw a parallel with drought and flood. In situations where you have drought, one should think of what you call devised methods of growing crops or plants in the light of shortage of rain. On the other hand, if you have a flood, then one needs to devise is how to make canals so that this flood can be used in the best way without destroying everything that's around. So that was the situation. I mean, for us statisticians, actually, it's a sort of challenge now, because earlier, during the time of shortage of data, statisticians have to deal how to estimate parameters in the light of shortage of data. Now, when this is a flood of data, the challenge becomes how to make maximal use of this without what you call damaging, like a flood damage, actually how to canalize it.
Without drowning in parameters.
Exactly.
That's fascinating. Does that mean that the mathematics involved is actually changing, that we're at a sort of
Yes.
cusp in statistics? Will somebody like you, who has been doing statistics for a long time, is that an interesting challenge, or is it like an exhausting challenge?
No, it's an opportunity. I would see it as an opportunity, actually. So I'm sure soon, in the coming few years, we'll see PhD dissertations or something written in this, how to handle big data or something. So this is a new challenge. That's how I see it.
What about Anders? How do you feel about this?
Yeah, well, I think Gebre put this very well, that I think we will see more interaction between sort of maybe optimization people and statisticians, because when you have this big data, there's just no way you can, I mean, you have to somehow take samples and work on samples, and then you want to say something about the whole as a result. And that's a big challenge.
I'm curious about optimization. What kinds of fields would you apply mathematics to optimize? Because my just experience of living in the world is that most parts of it and most processes you as a citizen and as a consumer and as somebody in traffic and so on, everywhere you go, it's incredibly not optimized. So I think there's a lot of work for you. But what kind of fields are you currently working in?
You work in it too. You take the shortest path to the bus, right?
Well,
you
yes.
know exactly which is the shortest path.
Yeah.
Now you can apply it to many. I mean, if it's sort of more technical, then it's sort of often more well specified. So if you go into more social areas, you can do it, but then it's much more complicated. For example, at KTH we have like a division making sort of urban planning, but then it's much more complicated because you plan for traffic, but the traffic is like a car with a driver, and the driver, you can tell the driver what to do, but he or she will do something else. So it gets very complicated. But you can do it in lots of areas. One
would suspect that there are areas in society where optimization would be very useful, but that nobody is interested in funding it, even though there is, in fact, somewhere a cost. I can't think of an example just now. If I can think of one, I'll get back to you. Okay. I'm just like dating. No, maybe that's not it. We have a question on Skype, I think. Do we have somebody there? Hello?
Hello, me?
Hello.
Hi.
Hi, what is your name, please, and what is your question?
My name is Forsgren. I am the CEO and co-founder of a company called Cefello, and we work with Bitcoins, the cryptographic money. And I was curious what the panel thinks of cryptocurrencies.
Cryptocurrencies. Do you have an opinion on cryptocurrencies? Anders is sighing. Would you like to begin?
No, I don't know enough about the subject to have an opinion, I don't think. In what respect should we have an opinion?
Whether it holds any promise for the future of money?
Or for the future of mathematics? No?
Well, I mean, it shows that, you implement some sort of mathematical algorithms to do this, and once you've developed it and made a program of it, then you can start analyzing what will be the consequences. And we don't know now whether it will work or not. I mean, we can't prove that it will work. In the mathematical universe, you can maybe construct a model of this, and then you can prove that this will be so and so hard to break through and to make not work. But in the practical universe, you can't really prove that it will be a success or not a success.
So there's
Bitcoin has a market cap of more than 9 billion already.
Right.
For now.
Yeah, but for now.
So, no, but then, yes, sorry, Anders.
No, it just depends so much on sort of what people. You have to make people believe in it. I mean, it's and that's the key. I mean, I don't think that we can, as much say, by math, say much. I guess it.
And then we're back to what David was talking about before, that there is the side of it that is about science, and then there is the side of it that is about emotions, right?
Yeah.
And Bitcoin operates not just as a technical system, but also in a financial market that historically has been very difficult to predict with mathematics. Can I ask you a question? Do you feel that people working with Bitcoin, do you have confidence that the mathematical abilities of everybody working with Bitcoin are high enough?
Well, the protocol in itself is actually an innovation that should be taught at any university. It has two different components in it that are fundamental. And the invention is one, decentralized money, which is the first time that it's happened. And it has created digital scarcity, which definitely, if you read the paper that Satoshi Nakamoto, the original inventor of Bitcoin, created, is very much an interesting paper that anyone that is involved in mathematics, I think, should read.
So without quite answering the question, I took that to be a yes. You think that you're pretty solid on the maths, you guys?
Yeah, I mean, the protocol itself, and then, of course, everyone that is involved in building the infrastructure on top of it doesn't necessarily hold the same mathematical skills to basically understand Bitcoin in its entirety. And a good example, if anyone has followed this, is the biggest exchange just collapsed and all the Bitcoins were stolen. So that's a good indication that the math skills with the people running the companies for Bitcoins are not yet in par with the actual skills that you're. I hear myself echo. Sorry.
Yeah, but that would still suggest that. I mean, and also, of course, with so many grad students watching, this suggests careers. Thank you so much for your question. That was interesting.
Welcome. Thank you.
Yes. Do we have a question from the audience? We've covered so many topics. Yes, please. In a way, I'm realizing now that this conversation is about the entire world. So the question could be on almost anything. Yes, welcome. Please state your name and ask your question, please.
Hi, my name is Clio Gonzalez. I'm indeed a Gothenburg student.
Hi.
I think that is missing like a bit of exciting about your examples of maths. My background is physics, and I'm doing like master on complexity science, which is mixture of computer science, maths, and physics. And I think that there are a lot of fun examples about statistics, like, for example, networks. I mean, you can apply networks, like talking about the brain, but also if you are recording the beat of your heart, I mean, you can like state things or talking about time series. For example, time series, you record the beat of your heart, but also if you record like the movement of the eyes of people when they are sleeping, you have time series. But also if you like, for example, talk about the market, also you have time series. So this behavior of the data you can analyze in the same way. So it's really exciting, how you can apply these statistical tools to analyze data that is coming from like a lot of things.
Vastly different things.
Yes. For example, returning to networks, like you can analyze how the subway is moving, and if what mathematicians call networks, like nodes, sorry. If one node is broken, then, I mean, people needs to move. So you can model in which way you can like transport these people in order to solve the problem. So I think that, I mean, there are like a lot of things. I'm doing my master thesis in psychology, so people don't know like really how to model the data. They have like really interesting data, but they don't know what to do with the data.
So that would, I guess what you're saying, this is a very good feedback point as well, that we should use more exciting examples. I'm sorry, did you have like an actual question?
Yes.
Yeah, sorry. Yeah.
So, sorry about all of this, but I mean, my point is, what do you think that is missing for involving more people into study physics or maths? Because a lot of people think that maths is boring or, ooh, they are scared about maths. But I mean, just like, I mean, last example, like physics is applied in doing like this fMRI when, I mean, physicists were people that create this fMRI machine, and you come up with a lot of data. So indeed, for like passing this data into the image of the brain, you need to do a Fourier transformation, which is maths, but at the end, in order to see the image, you are applying maths. So, I mean, there are like a lot of examples,
yes,
I guess.
Thank you. So, actually, I'm hearing sort of two questions. One is how do we communicate this excitement about mathematics to the population in general, returning a little bit to what we were talking about before. I think the other question is also, how do we take people in these other fields like psychology who are working, again, with very interesting data sets and say, hey, you should let's use some mathematics on this. We can help you find patterns here. Mats, you look like you have an answer.
Yeah, I think for the first question, at least, I think that we all have to do something, and it's about our kids. I mean, if we have kids at home, we have to talk mathematics, show them that we use mathematics, show them the joy of mathematics. The teachers in school have to show their joy of mathematics so that the students keep the joy and the enthusiasm. Because most kids like it when they're small, and then at some point they stop liking it, and maybe it's in 5th, 6th grade or something. And it's because we've stopped doing new interesting things. I think it's that, and also that it's not apparent that people around them are actually using mathematics.
Gebre, what do you think?
Well, I agree with Mats. And the other aspect I'm thinking is I'm not sure, but if it is a sort of mathematics, physics are sort of indoor subjects whose reward is not visible actually. I would like to suggest more like this actually on mathematics, where we can show, because other areas which we call soft sciences, like communication, media, style or something, they are more visible, they are more, I think, so people are exposed more partly through there. So I don't think we see the rewards and the outcome of mathematics, I think, in the media.
I think I should claim some responsibility because, of course, most people like me who are gatekeepers in the public space, we also don't understand the issues at all. We are idiots in the field of, well, all the hard sciences quite often. Not all of us, but typically that is quite common. So we are unlikely to point at the fMRI machine and say, look at the mathematics here, or even though we perhaps can make stories about the impact it has on health. We are not good at saying, here is the math, or here is the physics. We are telling perhaps the wrong stories. We need your help, I think. Anders?
Yes, maybe we have to do a better job. I mean, we teach the students, we send engineers out with good math, but maybe we should also try to explain better that there's sort of advanced math behind lots of things that people don't think.
David Spiegelhalter, final words. We're running out of time, I'm realizing.
About this. I think, it really irritates me when, an English journalist just wrote an article about, why is all this math so important? And I bet he's got a smartphone that he's using all the time. It just really irritates me, drives you mental. So I absolutely agree. You've got to ram it home to people. Just so these things do not just appear by people sitting around saying, "Wouldn't it be nice?" They've got enormous skills. Every time you see an animated film, there's a staggering mathematical achievements there. Every bit of technology we use. And that's got to be emphasized again and again.
Thank you. I just had this idea that maybe we should have math activists with stickers that say this thing contains math, and then the whole surface of the world would be covered, of course, in these stickers. That's not very helpful. We have to think of a better idea. Maybe our viewers can help us with that on Twitter. This is all we had time for tonight. We hope you enjoyed the program. Thank you so much, Mats Boij, Gebrenegus, Ghilagaber, Anders Forsgren, and via Skype, Professor David Spiegelhalter, and of course the Hovmöllers. Stay online for a chat with our professorial guests right now. Crosstalks will be back with a new live broadcast on May 6th with new exciting topics. Until then, be safe and be brave.